Hello, Mr. Russchenberg. Thank you for give a lecture to our university. I think we can wait for like 10 minutes to everyone to join us, and then we can start.
Excuse me, sorry, okay.
For everyone who just joined us, we are waiting for like 5 more minutes to everyone who are late to join us.
Colleagues, hello again. So I guess we can start. Ksenia Semenova.
She will start
please.
after 3 minutes.
Yeah,
Okay,
let's wait till 3:05. Hi everyone, let's start. It's a pleasure for me that we have this project as a start of our cooperation with Delft University of Technology. It is one of the best technical universities in the world. So many thanks to Professor Hermann Russchenberg for these 3 lectures. Today and tomorrow we will have lectures about radar technologies for investigation for research of climate change. In Ukraine currently we have a war, but we want to be global. We want to take part in all research processes, global science. Our professor of electronics department, Professor Felix Janowski, is currently working in Delft University of Technology as well. So I hope this lecture will be fruitful and useful for you. Professor Russchenberg, the floor is yours.
Well, thank you. Thank you for the nice introduction. It's my pleasure to do this lecture. Can everybody hear me? Is it clear? Is the sound okay?
Yes, perfect.
Okay, let me try to share the screen then. And everybody can see the screen?
Yes.
Yes, it's also clear. Okay, well, I'll talk, if I'm not mistaken, I have 2 lectures today, right? And 1 on Friday.
Right.
Tomorrow,
I said tomorrow. Yeah,
tomorrow.
2 lectures today and 1 on Friday.
Yeah, okay.
I just forgot one thing. I want to ask everyone to be active, to ask questions, to write questions in chat, and to ask questions at the end of the lecture. just get all you can from this lecture and from this communication with Professor. That's it.
Okay. Okay, now I will first talk about radar meteorology. So how can we use radar for meteorological observations? And I'll go step by step, I'll go deeper into the situation. First, I guess this is a picture you will all know, right? You will see pictures like this, rainfall maps measured with radar. You see them on the news, you see them everywhere. And they depict the distribution of rain in a horizontal plane. That's the typical thing you see also in the weather reports on the news. But there's much more you can do with radar, and that's what you can see on the next slide. This is using radar and LiDAR. LiDAR is a sort of radar, but then you use a laser beam to transmit a light pulse. It's reflected by the atmosphere, and you can measure the reflection again. But what we have over here are vertical cross sections. So the radar is looking vertically for 3 gigahertz, 35 gigahertz, and we have a LiDAR. And they look at the same passing front. So there's a cloud system passing over the radar. And what you see, well, it's different from 3 and 35 gigahertz, and it's completely different for a LiDAR. And that's interesting because we use these differences to understand what's going on in these clouds and what's going on in these systems. Let me see that. Can you see my mouse? Yeah?
Yes.
Yeah.
Yeah.
So typically this is time. So this a couple of hours over here in horizontal axis. Then we have the height on the vertical axis. Oh, wait, too fast. And it goes up to 10 kilometers. So what you see here, the upper part, that's a cloud system, and it's usually composed of ice crystals in the atmosphere. And here, this part over here, is a rain system. So rain falling out of the clouds and reaching the surface that you can see over here. And this red band over here is where ice crystals melt into raindrops. It's called the melting layer. Now this is at 3 gigahertz, and if you now go to high frequencies, 35 gigahertz, you basically see the same structure, but much more detailed. Certainly at the cloud top, right? You can see the top over here, these small blue patches, and you can see streaks over here. So 35 gigahertz is far more sensitive to what's happening in the atmosphere. But you basically get the same type of information, but more details. If you go to a LiDAR, so a laser beam, you transmit a laser beam into the atmosphere. Well, this is the same cloud system, but it's completely different. And the reason for this is straightforward. If you use light as your transmitting wave, then it penetrates far more difficult, so it has a hard time penetrating through the cloud itself. So it stops at this particular height, which is about, 1800 meters or so. At this particular height, where the LiDAR stops, we know from scattering theories that there's a water cloud over there. And water cloud absorbs all the light and nothing passes through. So it's empty over here, no signal. If you then say, well, let's have a look at this one over here. And what do you see at 35 gigahertz and what do you see at 3 gigahertz? At 3 gigahertz, you will also see this line over here. So also at 3 gigahertz, you pick up a bit of signal from the water cloud over there. This is just an illustration of how you can use radars in combination with other instruments to learn about what's going on inside clouds. And this lecture will be about the fundamental theories underlying these differences and how we can use them. So let's have a look at how radar works. So if this is your radar system, it transmits a wave to a rain cell somewhere. Of course, this cloud over here and the rain falling out of this is due to reflections by individual droplets, right? And all these individual reflections are then coming back to the radar and received over there. And we want to understand what's going on. So what you see in general, that the more droplets you have, the more rainfall there will be there. So high rainfall rates will lead to more water, larger droplets, more droplets, and the received power will increase. So more power, more rain. That's the main principle. But the question is, yeah, exactly, what is this relationship? Is this a straightforward relationship? So can we really link the received power by a radar instrument to the rainfall rate? And if we can, how should we do this? Well, for this, you have to go deeper into what the radar really does, right? And on the radar, well, it's a rather straightforward instrument. It transmits a wave. The wave hits a target over here. A bit of the target is reflected back to the radar, and it's received by the system over here. In mathematical terms, you can write it in just a couple of approximations. The received power over here, P received, is proportional to the transmit power. Well, that makes sense, right? The more you transmit, the more will be reflected. Times the properties of the antenna, it's the gain of the antenna, transmit antenna, receive antenna, times the wavelength of the signal that you use, squared. There's a term due to the loss on the way between the receiver, the radar, and the target. There might be some losses. And there's an R4 squared term, so it's dependent to the range to the fourth power. And you all lump this together into a straightforward relationship. Received power is C, and C contains all the instrument parameters. It's called the radar constant. The path loss, this term sigma, which is the radar cross section, so it's a degree of, it describes how much energy is reflected by the target. And this is the radar equation for simple cases. If you have one object reflecting targets. Then you have to describe first, if you want to understand how radar works for rain, because for rain or clouds, we're not dealing with one simple object. We're not dealing with one scatterer. We have many scatterers, millions in the raindrop, in the cloud. So you also have to understand first, what does one particle do? And second, what does a collection of particles do? Well, for this, you have to go back to the scattering theory. And well, suppose we have this incident electromagnetic wave. It falls upon this particle, the black particle over here. Then normally this particle, in a general sense, will distribute the incoming waves over space. Part of this will be scattered forward, part of this will be scattered sidewards, and part of it will be scattered backwards. So it will be distributed over space. It depends on the shape of the object and the size of the object, how exactly it will distribute the incoming energy over space. For weather radars, we used what we call the Rayleigh scattering theory for this. And that's a theory which says, well, the backscattering cross-section, so the degree to which a raindrop reflects energy back to the radar, is proportional to pi to the fifth, lambda, the wavelength, to the fourth power, the k term squared, and k is a term linked to the refractive index of the particle, so it tells something about the composition of the particle. In case of clouds, could say something about, is it rain, is it ice, that will be reflected in the refractive index, times the diameter to the sixth power. So what you see for the Rayleigh scattering, and the Rayleigh scattering is valid for particles much smaller than the wavelength, there's a very strong relationship with the particle size. And we will see later on that this is leading to problems. It's not something you like. But this is for one particle. So suppose you're dealing with rain, then so you know how one raindrop will reflect the energy by the Rayleigh scattering mechanism. Now, the next step is we have the radar volume, and that is filled with millions of particles. So that means that the total radar cross-section over here is the sum of all the radar cross-sections of the individual droplets. Now you have to sum up all the individual droplets in there. And that means, well, you can rewrite this. Supposing that it's all a uniform distribution, there's no spatial variation in there, you can say, well, the sum of all droplets in a cloud is the same as the sum of all the droplets per cubic meter times the volume. And then you can say again, well, the radar cross-section of the volume is this term, what we call reflectivity times the volume. And this term over here, reflectivity, that's an important term in radar meteorology. That describes really how rain and clouds and dictate how much radar is received, how much power is reflected by the cloud itself. If you look at this formulation, this one over here, there's of course this very important assumption from this step here to that step over there, that we assume that the raindrops inside the volume are uniformly distributed. Otherwise, you can't make this step, and you can't make this assumption. And that's also for many radars an issue, because the volume is quite large. It can be quite large, it can be hundreds of meters. And the rain itself, if you look at rain, then the rain has a very strong spatial variability. It can vary on a scale of tens of meters, which means that in many radars, this step already doesn't hold. And you have to make approximations for this. So what does it mean now for the radar equation? Because we saw the radar equation for one particle, and that was a straightforward relationship. But now we have to go for the radar equation for volume scattering, so volume filled with particles. Then we get something else. Again, this is the original that we started with. The received power is equal to the raised to the fourth power, or inversely proportional, times the total radar cross-section. Well, the total radar cross-section is given by this eta term, reflectivity times the volume. And we know the volume of a radar cell, and that's given by this term over here. And that's pi over 4 r squared, depends on the distance. The opening angle of the antenna is important. And this range dr is important. So that means that we get something a little different, we get a different relationship. The received power is pt, now the whole range over here, dr r squared. So now we have an r squared dependence times the reflectivity of the signal itself, the eta term over here. So the step from a point target to volume scattering, what we're dealing with weather radar, is also a step in range dependence. Range dependence goes from r to the fourth, so it decays much faster with space than the case of volume dependence, which is 1 over r squared. And if you want to do this properly, you want to also include the antenna beam itself. So many antennas have a Gaussian beam pattern. You can also correct for this with this 16 times the logarithm of 2 in there. But that's the detail here. And now we say, okay, we want to go one step further. And we get up to the term, what we call Z. And the Z is called the radar reflectivity factor. And that's the sum of per unit of volume of all d to the sixth in there. So the sum of all the individual droplets in the cloud times d to the sixth coming from the radar scattering. You sum them all up per cubic meter, and that's what you could. And then you get the term called the Z. And if you put this into the radar equation, you can say, well, if you have a properly calibrated radar, you can derive this term Z coming from the received power times the radar constant times r squared. And now we have something here which relates the received power from the radar directly to the meteorological properties, namely the particle sizes, the raindrop sizes in the volume. And that's an important step, but that's what we want to know. We want to know how the received power, that's just the terms in watts or so, is related to what you want to measure outside. And what you want to measure outside is not the received power, but you want to know how much rain is falling. And you want to know how much water do we have inside the cloud. Well, now we have a relationship that links those two. An important step is also, because I'm sure you have seen rain before, that the raindrops in themselves in a cloud are not the same. There's big ones and there's small ones. And this variation in particle sizes is given by what we call the raindrop size distribution. And the raindrop size distribution is, in many cases, it's given by an expression like this, an exponential distribution. Well, if you look at this, if you want to translate this into the radar reflectivity factor, the Z over here, well, the Z is, of course, in the discrete case, the summation of all the individual particles to the sixth. If you make the step to the continuous case and put an integral in there, you can include the distribution, ND, in there, the particle size distribution. Well, in the ideal situation, we now have, we can say, well, this looks a bit like a gamma function, right? So the well-known gamma function. You can simplify this by N0, the constant over here, divided by gamma to the seventh, that's this term over here in exponential, times the factorial 6. So, well, I can skip this. So now we have a couple of important relationships. We have a relationship between what the radar is measuring, the Z, as function of the particle sizes in the cloud. That's important. If you look at the liquid water content, so how much water do we have inside the cloud? And also here, it's linked to how much particles do you have, how many particles do you have in the cloud of which particular size. And that's given by this relationship. And if you look at the rainfall rate, R, that's also given by how much water, how many particles, how many droplets are falling to the surface of a particular size and a particular amount. And you have to include the fall speed, the VD, also in there. These are important relationships that relate the radar measurements, Z, the received power, to the physical properties of the clouds. In this case, it's linked to the liquid water content and linked to the rainfall rate in them. In many cases, if you do the statistical studies for these relationships, we can simplify this by a power law relationship by saying, well, the Z reflectivity values or reflection by the rain itself is linked via power law A to minus R to R to the power B, and R is the rainfall rate. So in the first simple approximation, you can now say, well, if I measure my Z, so I measure my reflectivity derived directly from my radar cross-section or my received radar power, via this power law, I can estimate how much rain is falling. This is the technique that has been done for decades. So do it like this. But of course, I went quite fast through the theory here. But in all the steps, you could have seen that there are many assumptions were made, right? Big assumption is it really Rayleigh scattering? Because Rayleigh scattering is only valid if the raindrops are smaller, much smaller than the wavelength itself. Is it homogeneous beam filling? So do we really deal with a uniform distribution of droplets in the atmosphere? Is there used particle size distribution, this exponential distribution? Is it the right distribution, or does it vary over time and over space? All these assumptions are in here. So over time, the last couple of decades, people have also looked into those assumptions and what's the impact of those assumptions. And one important step is that we can refine this by including things like polarization, and you will get that later today. One important step about Rayleigh scattering, you saw this strong dependence on the diameter d to the sixth. It's a strong value. It's a strong dependence. Because what it means is, for instance, an example like this. Suppose you would have a droplet of 1 millimeter, and to produce a reflectivity of 36, I forget about the unit from now, but produce the same reflectivity of 36, that is the reflected power by the radar, you would need something like 4096 of these droplets to produce this power. If you would have a drop size of 4 millimeters, then all you would need is one droplet to produce the same reflected power. That's only because of this d to the 6th dependence in there. And if you then say, yeah, but how much water do we have in 4,000 droplets of 1 millimeter? Well, that's about this value over here, 2144. If you would, how much water do we have in one droplet of 4 millimeters? It's much smaller. So you can see that this Rayleigh approximation has a big impact on the final retrieval of liquid water content and a final retrieval of the liquid water path. Because the same value, because of the strong dependence of particle size, leads to completely different estimates of the amount of water in the cloud. So you have to be quite sure about the assumption of Rayleigh scattering. You have to be quite sure about the particle size distribution that you use in. Well, and if you look at all sorts of studies about into the radar drop size and the drop size distribution, and you can ask yourself, how constant is it in fact? Well, these are histograms of the constants, and you can see, well, if it would be a constant, then these histograms would be a delta function, right? One spike for one value. But that's a huge range. So in nature, n0, so the constant of the exponential distribution is not constant. It varies over time. So then you get a question, yeah, so if our assumption of a drop size, of constant drop size distribution is wrong, how can we correct for this? How can we measure for this? And that's where polarization comes in. So for instance, if you look at ice crystals, or you look at raindrops or hailstones, different shapes or different form shapes, they all have a different shape, all of them. Ice crystals, they occur in a large variety of shapes, on plates, needles, and combination of those two. Well, hail is much bigger, right? This is just a few micron to a few millimeters, these crystals. Hailstorms can be much bigger, they can be centimeters, so they would violate the Rayleigh criterion. And raindrops, in the lower over here, they also have a different shape, because a raindrop itself, if it's the larger it becomes, the more air resistant it will experience from below. And that would mean that the shape would change. So small droplets, like the one in the middle over here, they would experience less air resistance. But as it increases, the bottom of raindrop flattens out. So the shape changes. And that's important, because with polarization diversity, so if you change the polarization of your radar wave, you can measure this. You can measure these changes. Well, this is a nice example of measured raindrops. So small drops over here near the spherical, and the larger they become, the more flat they also become. And these are photographs taken in the wind tunnel under controlled conditions. So if you look at a raindrop, so let's focus on raindrops for the time being, we also know that the axial ratio, A and B, so if this would be the raindrop over here, let's say it's a flat particle, then this axial ratio A over B is practically one spherical particle, small droplets, and it becomes much smaller for larger droplets. Particle size increases. And that's important, because if you use polarization in the radar, so let's say the one time you transmit a vertical polarized wave, and the next time you transmit a horizontally polarized wave, then the reflection for those different polarizations will be different. A vertical polarized wave, let's say for this particle over here in this direction, will give a smaller reflection than a horizontally polarized wave along this direction, because the particle is bigger. And if you can measure both polarizations, you can basically try to estimate the shape of those particles. And for raindrops, the shape of the particles is directly linked to the particle size. So indirectly, you also get information about the particle sizes. And therefore, you can refine your measurement of rainfall rate or liquid water content. Because again, it's linked to particle sizes. Well, here's an example of how this works. So this panel over here, the upper left panel, is the reflection of the vertical cross-section of the rain for horizontal polarization. And here we have the upper right panel. It's the reflection for the cross-polarization. So you transmit horizontal and you receive vertical like this. And then only if it's a very irregularly shaped particle, you get the signal back. And over here, this particle over here is when you measure vertical polarization. Now, what do we see in these images? Here we see, again, height 0 to 6 kilometers. This red band over here, this red part over here, around 1800 meters, is the melting layer. So that's where the snow from above, or the ice from above, so from above 2 kilometers, when it falls down, melts into raindrops below. And you can see, well, it's a strong reflection because melting snowflakes, they still are much bigger than raindrops are, and bigger particles give strong reflections. Now, a similar picture at ZVV, right? So, the vertical polarization. Lower signal, and the signal increases, and here we have melting layer and rain below. These two, HH and PV, together, if you take the result of this, the difference between those, produce what we call the ZDR, and that's differential reflectivity. And that's a term we will use to describe the polarization dependence of the signal. Well, if you zoom in, so here we have the ZH8 again. This square over here is zoomed in on the rain region below, right? Between it's below the melting layer over here. And from here, from the beginning of the box to the middle of the box, we see it goes from green to red. It basically means stronger reflection and more rainfall. And if you look at the differential reflectivity, the polarization dependence, and then you see, well, from the weaker part where there's no or weaker rain towards the middle, there's an increase of the ZDR. There's an increase in polarization dependence. Telling us also here, we zoom in a bit, also here in this part at 12, 13 kilometers, also here it's bigger than at 10 kilometers. If you go back here, 12 kilometers in the reflection and 10 kilometers green at 10 and red at 12. So reflectivity has increased. So what you see here, that increasing rainfall leads to a stronger reflection. At the same time, it also leads to stronger polarization dependence. That indicates that the particle sizes are increasing in size, and that's why we get the stronger reflection. And also the particles, the larger particles in there, are becoming more oblate, producing a stronger ZDR. So you can see now that if you have a radar and you include things like polarization dependence, you also get more detailed information about what's going on in the clouds and the rain itself. But again, go a bit deeper, because apart from identifying the increased raindrop sizes, we also saw that the shape of crystals, ice crystals, or the shape of snowflakes or hailstones are all also variable. And this leads to different polarization signatures. And that's also what you can see over here. So on the top, we still have low reflections, it's blue, it's all ice crystals. And ice crystals in the top over here, right, they are more oblate, or they come in forms of needles and small plates, and they give a stronger radar differential reflectivity. And that's what you can see over here, it's all reddish. Once they are falling down, they start to aggregate, they start to lump together, and the shapes get more fluffy. So on average, this means they become more spherical. And that means, well, the polarization dependence itself becomes weaker. But it's what you expect, because the particles have a less defined shape. And then in the melting layer, so here where it's red, this red part over here, we can see red and green in those boxes. And that is because the melting snowflakes in the melting layer, they produce stronger polarization dependence because they're more oblate. So if you look at the melting snowflake, I'm not sure whether you've ever looked at the melting snowflake, but if you look at the melting snowflake, you will see that at some stage the water during melting will be sucked to the inside and then slowly sent to the bottom side of the particle, snowflake, and then it will form a small liquid lens type of shape over there, leading to stronger differential reflectivity, a stronger polarization dependence. So by using radar itself, by looking at reflection itself, you can learn more about how much water do we have, right? Because there's a strong link between the degree of reflection and the amount of water that we have. You can also estimate things like rainfall rates, so how fast, how much rainfall is falling per unit of time. But you have to make many assumptions there about the particle sizes, the number of particles, the degree of beam fillings, how uniform or how homogeneous do we have this filling of the antenna beam. But you can do this. But the moment you include polarization diversity in there, you get into the domain of the detailed physics of observation. You can really look into the changing shapes of particles in the clouds and try to understand how raindrops are formed in the clouds. And I'll give you one example of also measurements we've done over here with the radar that we have in the Netherlands. And that's a case of an old case that we had a very strong event with flooding, high sea levels, leaking dams and dike, and also casualties. And the situation was like this. So I'm not sure whether you're used to reading weather maps, but this green, underneath the green dot over here, that's where the Netherlands are. And this red line is giving us the direction of a frontal system coming towards the coastline. And it's almost parallel to the coast. And this is a satellite image of the Netherlands. Over here, I'm here right now in this position where the mouse is. And you can see, well, the storm is approaching the coastline, and the tail of the storm over here is hitting the shoreline right now. This is a satellite image from space of the wind observations itself. And also here you can see, well, the Netherlands over here, and you can see the wind itself, a strong parallel component to the shoreline over here. It was a strong wind. And the strong wind was a very nice example of what we call a tsunami, a meteor tsunami. There's not a tsunami because of earthquakes, but it's a tsunami because of the varying air pressure. So low pressure and high pressure over the sea surface. But if you have a high pressure, well, it will push the water down. If you have low pressure, the water will come up again. In this extreme case, it led to a sudden peak of the seawater along the coastline, higher than the regular high tide that we had at the time. And so that led to what we call a meteor tsunami. But what did the radar see? And this is a radar observation. So the Netherlands here, and we have two radars, star here, star there, and these data were combined into one composite image. Here we have the storm front. And this red line over here is what we call a squall line. It's inside the storm. It's a narrow region of very high, intense rain. It's falling out of the cloud. And well, it's slowly approaching the Netherlands. See it now. You can see it's getting closer to the radar, and it's passing over the radar of the Netherlands now, and you can see how it passes over land. The line itself is breaking up in smaller segments, and that's because of friction with the land itself, and the storm starts to lose energy and it's breaking up. And then it's leaving the country afterwards. If we now go back over here, I have a couple of interesting things to see. So for instance, here it's still over the North Sea, and what you can see over here, that behind the squall line, reflection is quite low, right? That's what you can see over here. And if it gets closer, you start the reflection starts to increase. And if it gets into the middle, well, the reflection behind the squall line is even bigger. And this is because of attenuation. Because one thing I didn't speak about much is that radar signals, especially when it's high frequencies, will also be attenuated. And the stronger the storm is, the more attenuation you will get. Well, in this case, both radars are on this side, this here and here, on this side of the squall line. So it will be attenuated by everything. The signal from here will be attenuated by everything between the radar and the cloud over here. So, and here, on this radar will now only see if it's behind the squall line, and will not be affected anymore by attenuation. So you pick up the signals more easily. But that means that you also have to be careful if you make interpretations of radar data, because attenuation might play a role. Okay, now I have to find a movie. Let me see. I have to start in see where it is. Let's see. Stop sharing this screen and share another screen. This one. You can see this screen now. But this is a movie. This is going to be a movie of the radar that we also had in the middle of the two other radars, and which is pointing vertically. So this is measuring the vertical cross section of this passing squall line over land, and it shows very nicely how it behaves. So here we have heights of 0 to 5 kilometers. This is time, and this is horizontal cross section, and you can see the squall line is coming in. Right? It's over here, and here we have the 2 kilometers. You can see the melting layers, so where the snow is melting into ice. Well, the squall line, it's already over land, so it's broken into smaller segments. And it's getting closer to the point where the radar is also looking vertically. And that's coming, it's approaching center. Let's wait a while and I'll stop it. And now it has reached the center of the image. And what you now see here, while this squall line that we saw in horizontal image passing over the land, now we have on this stage over here, we have also measured with a vertically pointing radar system the vertical cross section. And you can see not only how it looks horizontally, but also how the vertical structure is. And what you can see nicely is that the squall line over here has this overhanging cloud system. And you might have seen this in the form of a shelf cloud passing over land and producing lots of rain. And you can also see over here the cloud part doesn't reach the ground yet, but after some stage behind the cloud, the shelf cloud, we have this rain downburst with very high intensity producing rain at the surface, right? From falling down from 2.5 kilometers to the surface itself, this red band over here. Now we also measure, I didn't explain this, the measurement technique itself, but we can also measure the Doppler effect, so the Doppler speed of the radar. And what you can see here that over this part over here, this part over here is falling down, that's the blue part. And here we have the red part, which is going up. So it basically means that what you measure, that in front of this cloud system, it's rolling over the countryside, and in front of it, it's producing vertical wind speed, picking up more moisture from the land itself, bringing it upwards, like you see over here. It produces a vertical wind. The wind transports water vapor upwards. The water vapor upwards feeds into the clouds, reinforces the cloud itself, and then the cloud can get stronger until it gets strong enough, and then it produces rainfall, and then for a long time it starts to rain afterwards. Yeah, and then the rain cell moves on, and then it stabilizes, and you start to see the regional, not entirely, it's a bit more turbulent again. You can see the structure with the melting layer starts to reappear again. So this is an example of, I'll stop sharing this screen and go back to the other one. Now, this is an example of how you can use radars or different radars together to get far more insight about the physics of how rain is formed, of how damaging storms can be. And to wrap it up for this part, so what you could have seen in this first part is that if you look at radar images and you combine the right models about the microphysics with the rain, so you have models about microphysics, models about raindrop shapes, and so on, you can really learn a lot about the physics in the rain itself. There's an example here. Again, this is time, we have height. We can see how clouds are composed of ice particles or even water droplets in there. We can identify how they melt into rain. We can identify the rain itself, what you see over here. But also, we can pick up drizzles of tiny droplets in the atmosphere, or clear air echoes. I didn't speak much about this. So this first part of today, I introduced briefly and quickly about what's going on and how can we use radar for different purposes. And in the second part, I will go a bit deeper into about the information content of these signals itself and how we can combine polarization and Doppler information really to trace down particle size information. So thank you for your attention so far, and then maybe a short break, or I can have a look at the questions in the chat. Okay. Shall I answer the chat questions now and then maybe have a short break? There's one question about, can turbulence influence the spatial orientation of droplets so that the larger droplet size will not be in a horizontal plane? Yes, that's a good question, and it can happen, because the reason why droplets, first, but the reason why they are oblate is the air resistance. And then they can get what we call a canting angle, so away from the horizontal symmetry axis, because of wind shear and turbulence. It can happen, yes. So in many cases, we also assume a sort of canting angle distribution to correct for this. In average, because you talk about turbulence here, turbulence can go in many different directions. This would still mean that the mean orientation will be zero, but there will be a variation of canting angles around the zero. The second question is the form of the droplets really so simple? No, it's not. It's a model, right? And models are always approximations of reality. But if you look at real raindrops, in many cases, they get close to what you just saw. But inside a raindrop, you also have oscillations. It's not a fixed, it's a fluid, so the fluid is moving inside the raindrop. And it needs, if the raindrop gets too big, you might get unstable oscillations in the raindrop itself, and starts to wobble a bit, it starts to move a bit. And it can even break up if this happens. So no, it's not that simple, but it's an approximation of reality that we can work with. I hope this answers the question. So then I propose to have a short break now, and then I can move on to the next one, if that's fine for you.
Let's wait, I think 10 minutes.
Okay, that's fine.
Die wil gaan donderdag. En dan hadden we ze ja gedaan. Ja, het is ja, maar dan heb je hebt ergens een half uurtje te eten en dan is het maar kun je nog wat doen? Nee, nee, maar hij zit dan echt zo een half uur of zo.
Maybe you can start again.
I think so.
Yes, I agree. So we can start. Please continue.
Okay, I'll start again then. So in the previous block, I discussed briefly and very fast gave an introduction to the concepts that we use. In the second part, I will go deeper into measurements we've done with radar systems at high frequency of cloud processes and how we can use those radars to understand more about the physics of cloud formation and cloud behavior, rainfall behavior. And to start with these two instruments. It's on the left over here. It's over here, this is a cloud radar working at 94 gigahertz, and this case it's looking vertically, so it's making vertical cross sections of the atmosphere. This system on the right is a dual frequency system, a cloud radar, and it has 35 and 94 gigahertz at the same time. And we can use those systems to learn more about what's going on inside clouds. I'll give an example first. This is a measurement of a couple of hours of the passing front over the radar. And there are many things in this plot that you can see. For instance, if you look over here, we have growing ice crystals. Well, you have to be careful here. It's very tempting to say that if you follow this path over here to say, well, this is all connected to each other. But of course, the radar is looking vertically like this, and the front is passing over like this. So in time, the measurements, the vertical cross-section that you do over here is not a cross-section of following the same particle. But the particles over here, at this height, might belong to particles over here sometime later, because time is passing in between those observations. So you can, if you look at this image, you can then follow the growth of particles as a function of time. Here we have this green layer on top of this. We have reflections by supercooled liquid. It's a very low reflection. It's minus 30 dBz. Forget a bit about what dBz represents. It's for this case, it's just a very low value. It's supercooled liquid clouds. And why do we say supercooled? Because they occur at a height between 5 and 6 kilometers. And at that height, it's freezing. It's below 0 degrees, far below 0 degrees. But still, we might have liquid over there. Over here, above, we have reflections by ice clouds, I think between 6 and 9 kilometers. Here in the upper lower corner, again, we have growing ice crystals falling down, and here at 800 meters, it transforms into rain. And you might recognize over here the sharp transition between orange and red. It's really a typical transition for these high frequencies, for 94 gigahertz in this case, between ice and rain. So, and over here, that if you look at these cases over here, you can see this cloud patch, something is falling out of the cloud, right? These green patches over here. But on the way, it evaporates again and never reaches the surface, and what we call a virga. And you can see them regularly in the atmosphere, so high level clouds, and it's something falling out of those, but never reaches the surface. Another example, so we have a low cloud over here at 1 kilometer, and some patches of strong reflection where some rain, light rain, drizzle we call this, is falling out. And also here, some patches of low reflection, and some increase over here, and some light rain falling out again. Here we have a larger system, it extends to 7 kilometers height, in which much larger rainfall is formed, which makes sense because there's so much water above it, in the 6 kilometers above the rain at the surface, above this transition zone. There's much more water available for the formation of rain. On the panel below, you can see this. This gives the rain rate measured at the surface with the rain gauges. Well, over here you can see, right, in this part, we have much more rain than in the beginning, but just, well, there's hardly any rain. And here in this third part, we have cold clouds, ice clouds, and falling out of ice clouds are again these patches of ice crystals falling out of the cloud but never reaching the surface because they evaporate again. So this measurement shows how complex the atmosphere can be. It's full of different types of clouds. Some rain out, some don't, and they all interact differently. So another example, if you look in more detail, is, for instance, here. You see that at the top of the cloud, we can see these patches, these falling streaks here. It starts here, and it's falling down, and over here, this time, it starts to produce rain. And this is an example. So at the cloud particles at 6 kilometers height, measured at 1230 UTC over here, they fall down and they produce rain at the surface, sometimes half an hour later. But really takes a long time before these ice crystals fall, and on the way down, they collect water vapor, they aggregate with other ice crystals, so they lump together, and in some states then they become big enough and they melt into raindrops. But it's a process of 20 minutes to half an hour. It takes a long time. We want to understand, can we measure the growth process of these particles on the way down by using radar? So what's happening in them? Another example of how instruments can look at these clouds differently. Well, similar to what I've started with. Again, on the right panel, we have a radar measurement with ice over here, falling down, producing melting snow over here, and then rain over here. The left panel is exactly the same cloud. The instruments were really close to each other, both looking up. And what you see, well, the LiDAR is picking up the strong reflection that the radar doesn't see. And this is strong reflection due to supercooled liquid. And there's some ice falling through the supercooled liquid through the cloud. If you put this on top of this, you can see over here a transition after the supercooled liquid over here, which in the same cloud happens in the radar image over here, you can see an enhancement, so from light orange to darker orange in the radar image. That is because the ice crystals falling from aloft over here, passing through supercooled liquid over there, grow because of the liquid in there. The liquid water that or freezes or evaporates and condenses on the ice particles and grow. And that leads to a growth of the ice crystals here, leading to rainfall down there. So can you really measure these type of, identify these types of processes with radar? Well, that's what I will talk about for the remainder of it. And then for this, you have to understand a couple of typical growth processes of particles in clouds. One is riming. And riming means, well, we have an ice crystal, could be a plate, could be a needle like this, and it collides with a supercooled droplet, really cold, below zero, water droplet in the atmosphere. And what you get then is a particle like this, right? The particle grows because of all the additional cloud droplets, water droplets growing on the ice crystal. You could also have what we call diffusional growth. That is, you start with an ice crystal, and then the water vapor, which is a gas, diffuses, so it basically connects to the ice crystal, it diffuses to the ice crystal surface, and then the particle also starts to grow there. And then in this process, because these water vapor molecules are quite small, the shape doesn't change that much, but the size changes, it grows. And what you can have is aggregation. So we have these particles, ice crystal here, needle there, plate here. They can lump together and make these larger shapes like this with irregular shapes. So what you see here, in the riming case, the well-defined shape of an ice crystal becomes more or less spherical because of all the individual droplets hooked on this. Diffusional growth leads to, well, it keeps the shape more or less intact, but the particle size itself increases. And aggregation, well, the well-defined shape of plate or needle basically turns into, on average, a spherical shape. And this is something that you might be able to measure. And for this, we have to do a clever trick. And the clever trick is to combine polarization measurements with Doppler speed measurements. And for this, there's one thing to understand, that if you look at a cloud, or let's say a couple of particles in the cloud, that not all particles have the same fall speed. Some might fall faster than others. And in case of rain, this is a straightforward thing. A small droplet has a lower fall speed than a large droplet. And the larger droplet, faster it falls. It also will have, the larger droplets will also have a larger radar reflection. Because of this radio scattering mechanism, d to the sixth, but also in Mie scattering or higher frequencies, this relationship holds. So there's a combination, or at least a relationship, between particle size and particle speed. Well, if you saw in the previous graph, there's also a relationship between particle size and particle shape. So if you now are able to measure both, so the speed of particles and the shape of particles, you can learn more about how the shapes are changing as a function of particle size, and because it's all linked. That's what we do with what we call spectral, Doppler spectral studies, spectral polarization studies. So what we do, first we measure what we call a Doppler spectrum. And Doppler spectrum is the velocity spectrum of all particles. I won't go into details of how we measure this, but this is what we can measure. And then you do this with different polarizations. So you get a velocity spectrum for horizontal polarization and vertical polarization. And then you look at the difference of those two. So you get information about polarization dependence plus a function of every particle fall speed. You basically get the polarization dependence for individual particle types and particle sizes. That's powerful. They really can connect all these things. So what you can expect, roughly speaking, so in case of rhyming, if you start with the same velocity distribution of velocities over here, so basically you say it's the same particle size distribution for different cases, and we follow the rhyming. Well, if you start with this particle size distribution, the velocity distribution, and we start off with this initial distribution of the ZTR, so the particle shape, small particles over here, so the spherical, large particles, mass. Large particles here, so more oblate. Well, because of the rhyming, this transforms in a signature like this, different Doppler spectrum, and the particle, the shape itself changes because of this relationship. The same is true for diffusional growth. You start with the same particle size distribution, but because of the underlying assumptions you made about how particles grow, you start to expect a different Doppler spectrum. And that's the black line over here. And we can expect a different shape relationship with the function of the velocity, because every individual particle will interact differently with all the water vapor around it and changes its shape differently. And the same is true for aggregation. So we start a different distribution. Because of the aggregation, we get a different distribution resulting velocities of the particles and a different distribution of how the particles are shaped as a function of the size. So this is something that you could expect qualitatively based on theory, and you can also try to measure it. And we've done this in this campaign with radar over here called the TARA system, radars over here, high frequency systems, another radar over here, so a couple of systems together. And I will go through one example of this campaign. Here we have 4 plots. The upper one is the reflection of the vertical cross-section at 94 gigahertz. Here we have the same cloud, but then at 3 gigahertz and at a different elevation, so we can measure the polarization dependence. Here we have third panel is the polarization dependence, and here we have of at 3 gigahertz, and here we have the polarization dependence at 90 gigahertz. So we have 4 panels coming from 2 instruments, and we get reflectivities and we get polarization dependence. Here we have a radio sonde measurement, so we also launched a balloon into the atmosphere to measure temperature profiles and to measure dew point profiles. From this we can retrieve where we can expect clouds. So when the red line and the blue line are the same, it means the dew point and the dew point is equal, we can expect condensation and therefore we can expect clouds. Now that's at 3.8 kilometers, 6 kilometers, and 7 kilometers. So here where the arrow is, and that's where the arrow is. We can also expect water clouds. So let's zoom in, see what we get. If you go to the first part, so go back here, so we analyze this part over here. What do we get then? Oh, this is the segment of the first part over here. What we do, first we say, well, does it really have an impact if we analyze a vertical line like this, which is the most easy one, because that's a measurement you take, or if we follow the black line like this, and that's the line by which we expect the particle will fall as a function of time. Well, on the left panel you can see the difference. Here we have the reflectivity. For the black line over here, if you follow this black line over there, and the magenta line, if we just follow the vertical line like this time over here. And you can see, well, they're different. Well, that's what you expect, right? So, but it also has an impact on the corresponding polarization dependence of action. And that's what you can see in picture D, because picture D here is the polarization dependence again. Black line is after following the fall streak path, so how a particle is falling. And magenta line is if you just follow a straight line over here. And yeah, indeed, there's a big difference between those two. And the black line is then more accurate than the magenta line. But now, what's the information content in these panels? What do we see? First, if you look at the N, this region over here, N, you see that the black line, so the where we started to fall in the particles, has a strong polarization dependence over here. Which means that particles over there are oblate, flat particles. And that coincides with the presence of flat ice crystals. So it's basically a region where the ice crystals are formed in the atmosphere. That's why we call this N, that's the new particle formation. I won't go into the details of how particles are formed, but at some stage, the water vapor has to transform into particles before you get a cloud. Well, that's what we see at the N region. So the radar is picking up the parts where new particles are formed. Now the particles are falling down again. Well, and you see that while they fall down, over here for the black line, the polarization dependence decreases. So this flat shape that it had originally becomes more or less spherical shape, right? And then ML stands for melting layer. The spherical shape, well, gets a peak, and because during the melting, get more water in there, and the water sinks to the bottom of the particle, forming this lens, and then you get larger settling. And then below the melting layer, well, you have this pattern over here. What you expect to be the values of raindrops. So this panel, panel D, shows us where we have new particle formation. If you now go to panel F over here, and this is panel F is an interesting one because it shows the Doppler spectrum itself. So it shows the variation of fall speeds in the cloud, in the rain, in the melting, in the cloud. And what you see here is that in this cloud part over here, above 2 kilometers, the variation in fall speeds is quite narrow. So the particles over there in the cloud have more or less the same fall speed. They more or less fall down regularly with the same speed, not so much variation. As they fall, well, you get a larger variation in fall speeds during melting. And that makes sense because some particles will melt, well, turn into raindrops, get a fast fall speed, and some particles are still melting and still have their low fall speed. So you basically spread, and you make the distribution of speeds wider. And then the blue part over here, well, we have a wide distribution because the variation between particle sizes in rain, very small droplets and large droplets, much larger than the clouds itself. So already this distribution of velocities that you can measure with the radar gives us lots of information about the physics in the cloud itself. Now this is the image of the polarization dependence. And if you look at the top over here, you can see a very small orange part. And this orange part is where the polarization dependence is large. And secondly, that's a part where the new particles are formed before they fall down towards the surface. So there's lots of information, there's more information also in the other panels. So there's lots of information in the polarization dependence of the signal, but also of the velocity measurements that you can do with the same type of radars. They can analyze how particles are formed. So what does it mean? Well, we saw that at the cloud top, we had this, so here we have a cross-section of the Doppler spectrum at 3.2 kilometers, 3 kilometers, 2.8 kilometers, and 2.5 kilometers. First, we see that the spectrum itself changes in value, right? It increases. That makes sense because particles are getting bigger in the cloud and you get a larger variation of fall speeds. So that's what you see, increased particle size. If you look at the particle shape, well, the cloud top, it's increasing its particle size. So small particles But spherical, no real polarization dependence. Larger particles are more oblate. And this is at the height when new particles are formed. But if you go down, you can see that, well, that basically this ideal shape over here, it flattens out and becomes almost spherical at the cloud top over there. So you see the transition from oblate particles, so flat particles at the cloud top, to spherical particles at the cloud base. And this is a typical case of what you can expect in case of aggregation. So by doing these type of analysis, we can also identify what sort of growth mechanism is happening inside the clouds. And we can do this also for other clouds. I'll give you one more example over here. So if you look at this is another cross-section at another time in the system. And then, for instance, focus on this part over here, panel F. Now, in the previous panel, we saw this new particle formation only at the cloud top. Now we see the whole range over here at the side of the spectrum with a larger polarization dependence. And it gets smaller if you go to the left over here. So there we have a whole range of particles, ice crystals, for a larger part over a range of at least 1 kilometer. But it's a new case of new particle formation at a different height, different location. So in clouds, the growth mechanisms and the initiation mechanisms themselves are not constant, and they vary from time to time and place to place in the cloud itself. And I can skip through all this because that will take too much time. So by this combination, you can see already that the combination of polarization and power and Doppler is a very powerful combination to analyze cloud physics and cloud physical phenomena. Other example, this is still a bit speculative. If you look at 35 gigahertz radar, can you also identify thunderclouds with this? And here we have, a radar reflection, part of this. And this part over here is interesting. But this is the differential reflectivity again, the ZTR, the polarization dependence. It tells us something about the shape of particles. And as long as it's green or red, it all means it's oblate. So they're larger in horizontal extent and in vertical extent. But now we have this blue part over here in the cloud, which is the opposite. So instead of being flat like this, it becomes more and more elongated particle like this, with a vertical dimension. So what's causing this? What's going on over here? Also here we can dive into the variation of velocities as function of height. And here we have refraction, and here we have polarization dependence again. And if you look at 0 meters per second, then blue negative means towards the surface and positive means upward wind velocity. So there's also a different wind direction on both sides of the 0 meters per second. And this is the blue part we were just discussing, just talking about. So apparently the blue part over here is linked to something falling down. And the green part over here in the same cloud at the same location, there's also something going up. Right, so this part over here, what's blue in total over there, consists of two parts. One part going up, going down, and one part going up. So in this volume, we have competing mechanisms, going down, going up in the same volume. And we can identify those dynamic patterns with measurements like this. Now, negative ZDR, the polarization dependence that you see over here, is often coincides with what we call Kraupel. So soft hail it is. And this Kraupel has, in many cases, a conical shape like this. So it peaks a bit towards the top. And this would lead to a negative polarization dependence. I can do all sorts of simulations over here. I can skip those simulations, it's too much detail for now. In the end, it comes down that we have negative of falling down velocity, upward velocity, and these competing particles. So we have falling gravel, and yet ascending ice crystals over here, positive ZER. Well, if they collide and they aggregate on top of each other, you're producing a strong hailstorms again, because the particles will grow because of this. And it's also something you can really identify if you have this combination of polarization and of Doppler measurements. Well, that's so nice animation. That's the story. I want to go a bit deeper into what you can learn from multiple frequencies. And that's an example over here. Again, this is 35 gigahertz, and this is 45 degrees elevation. 3 gigahertz, 45 degrees elevation. And yeah, you can see a bit of a cloud over here, a bit of a cloud over there, melting layer over here, and some rain falling out over there. But you can also see it doesn't see, you can already guess over here in this plot that it doesn't see everything and there's something missed. And if you say, well, what would a 35 gigahertz look like in this same situation? You get this. That's a much fuller picture. And the reason for this is just sensitivity. There's a big difference in terms of sensitivity for short wavelengths, so high frequencies, and long wavelengths, the lower frequencies. So the S-band is picking up signals, of course, up to 7 kilometers. But in this case, the 35 gigahertz is also picking up reflections from much higher, right? From up to 10 kilometers. So you can ask yourself, if we see in the S-band, we see the cloud and we see no rain here, and the same cloud, we see rain over there, then this radar itself will not give you the answer, will lack data. But if you combine this with other sources over here, you get a completer picture. And you can say, oh yeah, well, I see there's much more going on in the atmosphere. How can we combine this? What can we learn from this? So, to make it complete, you can also say, well, let's include a LiDAR, right? There's a laser beam in there. What would the laser beam see? Well, that's what you see over here, these red lines, right? Are lines where the LiDAR, so a laser beam, picks up reflections from the atmosphere. Well, you can see that in many cases it's picking up something that the radar doesn't see. That's 3 gigahertz. If you go to 35 gigahertz, well, the LiDAR is picking up signals, but the radar is also picking up signals. That means that at this particular height of 5 kilometers, again, we are dealing with supercooled liquid clouds. Supercooled liquid clouds are composed of small particles, around 10 micrometer, and in many cases they're too small to be detected by a radar for low frequencies. If you go to high frequencies, shorter wavelength, they become sensitive to these clouds. You can pick them up. So you see the red line over here, the cloud over here, so indicating liquid water clouds. Here, where the radar is really picking up a cloud signal, the LiDAR signal is gone because the cloud below over here is too thick for the LiDAR to penetrate. It doesn't see it. And here the red line appears again because, well, this part over here is apparently thin enough now for the LiDAR to penetrate. So then you get the question, why is it thick here and thin over there? Well, that has to do with the optical thickness of the cloud itself. So how much space do we have between the droplets? How many droplets do you have in there? And is it ice or is it liquid? Now on the right panel, you can also say, well, if you look at the polarization dependence of the 35 gigahertz, we see these lights or these striking features over here, where we have a larger polarization dependence. So this means that there's something more oblate particles, crystal types over here. If it's red like this over here, the polarization dependence itself is very small, right? And that means spherical particles. In a 3, the magenta over here, we see this narrow line again of high polarization dependence, and that leads into the direction of melting particles. So again, lots of information about the microphysics in the cloud. I can combine all this because now on the right panel, we also have the polarization dependence from the 3 gigahertz. And you can see, well, yeah, with the 35 is picking up oblate particles. Also, the 3 gigahertz radar is picking up oblate particles. So there's so much information in these systems that you can really describe the state of the microphysics inside the cloud itself. And you can also, by connecting all these information sources cleverly, you can also then describe the growth processes inside these clouds and how rain at the surface actually forms. And then we have a final result of this. The liquid clouds over here, well, the liquid clouds, the ice over here is falling through liquid clouds, right? The number 2. And while they do this, they grow, so the particles are getting bigger. And also here, and while they get bigger, well, they fall down and they produce this blob over here. Here, and it doesn't fall down because there's not enough ice crystals to form. Here, we have liquid clouds over here, we have some dashed line over there. We identified ice crystals to start with. Well, these ice crystals already have the potential to grow, and they fall with this liquid cloud layer here at this particular height. And when you do this, apparently the addition of this fall streak at this particular height, the combination with what we have over here, is giving enough potential to get the rainfall formation at this particular location over there. So this story tells us that we can also, by looking at these observations, explain why the same cloud, or let's say same cloud system, can produce rain on one occasion and not produce rain on the other occasion. It's all linked to the presence of liquid water inside the cloud itself, and we can pick this up with a LiDAR system. Now to wrap it up, and then maybe time for questions. We do all these measurements in the Netherlands as part of what we call the Ruisdael Observatory, which is a national observatory with many instruments across the whole country. In the city of Rotterdam, we have instruments at the observatory in Cabau, at the heart of the country, in a forest area called Lobos, where we have instruments, and in the north of the country, where we have instruments, should we look at all these phenomena. And the reason why we do this is that along these measurement sites, on one we start with the North Sea, that's the where Rotterdam Harbor is, but then we can follow these parts, you can see it over here, we can follow these stations onto the north, and then where it leaves again back into the ocean. And this is also the prevalent wind direction that we have in the Netherlands. It's southwestern wind. So it means that we pick up the air mass coming from the North Sea, we measure everything in this air mass, and we follow this over land until it leaves the country again over sea. And we try to identify and understand the changes it's undergoing while it's passing over the country, and then identify how the weather system itself is interacting with the land surface and the city surface and the forest areas over land, and how this modifies the cloud system and the rainfall formation. And with this, I want to end the second part. And I'm not sure whether we have enough time for questions. So if you have any questions, please go ahead. Are there any questions? I cannot see the chat anymore.
I'm sorry, may I ask one question?
Yeah,
I'm from the electronics department. So you have described the model of the shape or form of your droplets. And you have very maybe simple model of these droplets. But it seems to me that in real life they are more complicated. How you connect this, maybe your simple model with the real shapes of the droplets?
Yeah, that's a good question. Indeed, real life droplets are far more complicated than, and certainly the ice crystals are far more complicated than what I've just shown here. And we simply don't have enough measurements to take all these detailed variations into account, right? So we have to make assumptions for this. The only way you can deal with this is by including error bars in your final results. So what is the consequence of making this simplified assumption? The moment we would have more detailed information on the measurements about the shapes, we would include it. But so far we simply don't have it. So we have to make these assumptions. And then assume, and we then include this in the error estimates that you have in the end.
Thank you.
Yeah.
Sorry, I would like to make a question. My question about possible cooperation between your university and the National Aviation University. Is it possible for our students to have some kind of internship in your university?
Yeah, we do not really have an internship program, if that's what you mean. Of course, we have ad hoc programs, right? There's not a real program for internships, but we can always try to arrange something in an ad hoc manner. So in that sense, it's best to contact me or somebody else to see what can be done to make this happen, if you want this, something like this. But best to contact me separately.
Thank you.
More questions?
One more question, if you, I don't know, do you see me because I am
I can see you, yeah, I can see you.
Yes,
I can see you.
that is great. So you have different models for different, not models, but results of investigations for different frequencies, different radars, and how you connect in one model these different measurements, because I don't understand. Yes, of course, I can look at the picture, but the picture is something manually investigated. How can we make some algorithm in order to understand what we have? Ice here, for example, rain, or something else. Do you have some?
Yeah. Well, that's a good question, and there are several methods for this, classification schemes for this. The best example, if you really want to see examples of this, is if you would go to the database of the Actress program. I'll type it in the chat here. It's in the chat, and that's a European program where you have a database of ground-based observations of clouds. And what they do, well, what we do there is we combine different instruments, so LiDAR, radar, microwave radiometers, many more instruments. And based on this, based on the underlying scattering mechanisms, the scattering theories, we produce classification plots so that you can identify where do we have liquid, where do we have insects, where do we have rain, ice, and fog, or whatever. And the underlying physics is always the scattering theory. And that ranges from Rayleigh scattering to Mie scattering to scattering by different ice crystal habits, optical scattering. That's the underlying theory for all cases. And on the Actress website, you can find detailed descriptions of the underlying algorithms to make this. What you also see now, and that's more recent, is to use machine learning techniques for this. So you simply train a neural network to do this classification for you. And that's a completely different approach. But it's also available in the open literature. You can simply download the codes there. It's called the voodoo approach.
Mhm. Thank you, I understand. But maybe you can use simple statistical description of your experiments and measurements, and use some statistical theory, which is widely used for many years for the classification of different objects.
Oh yeah, yeah. Well, statistics is not that different from machine learning, right?
It's slightly different thing, I think.
Yeah, okay, okay.
Thank you.
Sorry, could I make one more question related to your last answer? Do you have some open source data, for example, to try to make some machine learning, to test some machine learning algorithm? Do you have in the open access such data for open for everyone, researcher?
Again, if you go to, depends a bit on what you want to do, right? But all the data in the Actris database, that's open. Everybody can download the data there. But that's already data in the form of data products. If you want to go to the raw data, underlying raw data, yeah, then I think it's best to contact me again, and because that's much larger. That's a much larger database to download. But if you want to start simple with data products and go to Actris first and download the data from there. And if you want more, just contact me again.
Thank you very much.
Colleagues, any other questions?
Yeah, one more question. KPI military department. I have some question about machine learning. That analysis of radar cross section of the meteorological objects and extrapolation of data.
I didn't hear the question.
Radion, your connection is not so good, so please repeat your question. So,
my question is about interpolation of changing radar cross-section data by machine learning. Is there some? Is it realized by machine learning?
Oh, okay. I don't know, actually. I don't know. I'm sure people are working on this. But I don't know whether this is realized already.
Because this part of analyzing and extrapolating is important in all for radar systems.
Yeah,
I think that we have some. Okay, thanks.
I think there are no questions.
Okay, that's good because I have to leave in a couple of minutes.
Yes, but it was very, very amazing lecture. Thank you for this. On behalf of National Aviation University, as a Dean of Faculty of Air Navigation, Electronics and Telecommunications, I would like to thank you very much for this fruitful time, for these very interesting lectures, presentations. And of course, I hope that we will meet offline sometime in walls of National Aviation University. We agree to meet in your host institution, but at the same time, we wish to finish the war. We wish to win and to invite all of you, and you will be invited definitely to our university. So thank you again, and we hope to set up a fruitful collaboration for both institutions, and to remind all of present people, representatives of National Aviation University, other institutions, that we will host the next lecture with Professor Russchenberg on Friday. So everybody is invited there as well. And we will continue the discussion of this very interesting and important topic. Again,
And I would
thank
like
you.
to add that the last
yeah.
lecture will be the most interesting because it is data fusion, synergy of different sensors and so on. It is much more general thing, not only related with atmosphere, but it is experience which can be used in many other fields. I'm sorry for interruption. Continue, please, Roman.
Thank you, Professor Janowski, for building this interconnection between our institution and Delft universities.
Will you share material?
If Professor Rauschenberg is don't mind, so we can share it because we have made the video recording.
Of course, no problem.
To all the registered participants, we will send the link to this lecture.
Okay, that's
Lectures.
fine. Yeah, that's fine.
With slides?
And Professor Rauschenberg, question regarding the slides. Can you send the slides?
Yeah, I can do this. I can maybe do this on Friday when I finish the whole thing. I can send a package of slides.
Yes, okay, thank you.
Okay,
So, okay, I think that everybody is a little bit tired, so we can close the session. Thank you again, and see you on Friday. See you all.
My pleasure. See you on Friday again.
Yeah, goodbye.
Bye.